Okay, so we're going to introduce energy into our discussion of simple harmonic motion and periodic motion in general. So the impetus for this is that the spring force is a conservative force. So if it's the only force doing work, then energy should be conserved. There are a number of slides, as well as a number of examples and figures in the text. When no non-conservative forces like friction do work, when friction doesn't do work, the energy should be conserved. Okay? So we're going to think a little bit about what that means. Okay? You're also going to be introduced in a little bit more detail to the pendulum and the physical pendulum. Okay? So when you look at and think about the motion, certain things don't affect the period. So for instance, in the spring, be clear about what affects the frequency, right? Is it how far I pull the spring back? Does that affect the period of the motion? What about the spring constant? What about the mass? Okay? What affects the timing of the spring? Same thing for the pendulum, right? When we displace the pendulum just a little bit, what affects the period? So this is a grandfather clock. What affects the period of the motion? Is it the mass that we put on the end? Is it the initial displacement? Is it the length? Is it some other constant that shows up in there? Make sure that you're clear about that, right? Because those are going to be things that you're going to want. We'll eventually write them down and you'll use them on an equation sheet at some point. But what affects the motion? In the last section, we introduce a little wrinkle and we say, all right, let's take our spring, but let's add a little bit of kinetic friction. Kinetic friction, oh right, that's a non-conservative force. So the takeaway is that force is going to do negative work to change the kinetic energy. So as the spring goes back and forth, what happens to the motion? Pay particular attention to the plot. In this slide, this is one of the pre-class slides, but we've talked a little bit about what the motion looks like. Now, part of the deal you struck with me is we don't have to do any calculus, but you have to take the model that I give you and do stuff with it. Well, we're going to do that here. When you look at these two figures on the right, what's happening is the amplitude of the motion goes down. Friction does negative work, and so that has an effect of decreasing the amplitude of these sine waves. The period doesn't change, but what's happening here? Well, those maxima and minima are decreasing in what we call an exponential envelope. There's an exponential decay on the maxima and minima. We're going to spend a little bit of time with this in class, not too much. Okay, you're going to do a homework problem or two. But again, we're applying a model, so you just have to get good at it, taking what I give you and trying to apply it. Okay? Be happy to go through the derivation with you. It's pretty straightforward, but it requires a little bit of math. Okay, so if you want to go, if you're not satisfied with the damped harmonic oscillator, what I give you, let's go through it. Okay, it's not that hard. As always, take your time. This is important stuff. Oscillations, energy, these are things that are going to show up again through the remainder of the course. Okay? Come and chit-chat whenever you need.